Hello, in this chapter, chapter 7, we're going to go over energy and chemical processes. So on the right, I have what's called a phase diagram. And this is just showing that if we start with ice and we heat it, so temperature is on the y-axis and heat added is on the x-axis. If we heat the ice, it eventually melts and turns into a liquid. And if we keep on heating that liquid, that eventually turns into a gas or steam. So we're going to go over the exchange of energy in order to help melt that ice. So we'll go over that later on. But first, let's get into some definitions. So energy. We use energy all day, every day. We need food in order to provide that energy. Now, if we think about in humans and animals, we all have what's called a metabolism. And metabolism is the term for the chemical reactions that occur in our cells and provide energy to keep our cells going, to keep our cells alive. Now, some of the energy from metabolism is in the form of heat, and some animals use that heat to regulate their body temperatures. Now, bears hibernate in winter. So what happens when they're hibernating? Well, they don't really need a lot of energy, so their metabolism and body temperature will decrease during that time when they're hibernating. And hedgehogs also hibernate in winter, so they do the same. Now, in dogs, the average body temperature of a dog is about 4 degrees higher than that of a human. And instead of sweating like humans do, dogs will pant to rid themselves of excess heat. So we all use energy in different ways, but let's actually talk about the definition. So energy is the ability to do work. And energy, of course, can be transferred from one object to another if the objects have different temperatures. Now, this transfer of energy due to temperature differences is called heat. So this seems really basic, right? We cook, we see that transfer of energy if we're cooking. We also can feel that exchange of energy or heat if we hold a hot cup of coffee or tea. So same thing here. Now down below I have a picture of hot dogs grilling. So heat is transferred from the grill into the hot dogs, and that's what cooks them. And then of course we eat the hot dogs and we gain energy from the food that we eat. Now, with energy and work and heat, we do need units, right? So the SI unit of energy, work, and heat is the joule, which is given a capital J. And a joule is a pretty tiny amount of energy. So for example, if we had 1 milliliter of water, which is really small, and we tried to increase its temperature by only 1 degree Celsius, it would take about 4 joules. So it's not a lot of energy. And there is another unit of energy that you might be more familiar with, which is the calorie. And this is given the abbreviation CAL, all lowercase. Now, 1 calorie is equal to about 4 joules. More specifically, it's equal to 4.184 joules. Now, we're used to seeing calories on nutrition labels. So for example, off to the right, I have an example nutrition label. And whatever this food is, 1 serving size is about 60 calories. But notice we're using a capital C here. So if you use a capital C in calories, that is equal to 1,000 lowercase calories. And we could also call that a kilocalorie or kcal. So on this nutrition label, it's actually about 60,000 lowercase calories per serving, but it's a lot easier to list things in kilocalories on nutrition labels. So let's practice doing some conversions. Let's look at an example of an apple. So an apple is about 95 capital C calories. Let's convert that amount to lowercase c calories, and then we'll convert that into joules. And I have the conversion factors or equalities up above. So see if you can do this on your own first, and then we'll go over it together. All right, so let's start by converting 95 capital C calories into lowercase c calories. So I want to multiply this by a conversion factor. Again, if you use train tracks or another way to solve this, that's totally fine, whatever works for you. So I'm going to use the first equality up above, where 1 calorie, capital C, equals 1,000 calories, lowercase c. And since we're converting to the lowercase calories, I'm going to put that in the numerator, and I'll put 1 capital C calorie in the denominator. All right, so capital C calories cancels, and we get 95,000 lowercase c calories. Okay, so now in the next step, we want to convert that into joules. So I'm going to use the second equality, where 1 lowercase c calorie is equal to 4.184 joules. And since I'm converting to joules, that will go in the numerator, and 1 lowercase c calorie goes in the denominator. So the lowercase c calorie cancels out, and we're left with joules. So my calculator gave me 397,480 joules. However, we were given 2 sig figs in the beginning. So let's limit our answer to 2 sig figs. So what would be an easy way to do this? Well, if we round up, we would get 400,000 joules, but this doesn't really tell us how many sig figs we actually have. So instead, let's use scientific notation, because that's going to express how many sig figs we have. So let's say we have 4.0, because remember our coefficient has to be between 1 and 10 or equal to 1. And then how many times would we need to move the imaginary decimal point? Let's see, so once, twice, 3, 4, 5 times. Okay, so this would be our answer with the correct number of significant figures. So 4 times 10 to the 5th joules. Okay, so hopefully not too bad, especially after last chapter where we did a lot of conversions. But let's move on to heat and temperature. So temperature is a measure of how hot or cold an object is relative to another object. So this could be referred to as the object's thermal energy content. And heat is the flow of thermal energy between objects with different temperatures. So for example, down below I have someone holding a coffee cup, and heat from the coffee is transferring to the person's hands and surroundings. So that's going to be the flow of thermal energy from the coffee to the hands. And we can measure the temperature of the coffee using a thermometer. So that would be a measure of how hot the coffee is relative to another object. Now, we do have 3 different temperature scales that we can use. In the US, we use Fahrenheit. Most of the rest of the world uses Celsius, and Celsius makes a lot more sense when we break it down. And then there's one other unit of temperature, the Kelvin scale. So the Kelvin scale is really useful because all of the temperature values are positive. And this is going to come in handy later when we're doing some equations involving temperature, because if you have a negative temperature, sometimes that can mess with your equation. So having a scale that is all positive values can be really valuable. Now, off to the side I have here, temperature is a measure of the average amount of energy of motion or kinetic energy that a system contains. So in that coffee cup, for example, the coffee had energy. The little molecules were moving around in there, and as it cools down, the kinetic energy decreases. So the temperature decreases. All right, now let's compare these 3 temperature scales. So in Fahrenheit, we have the freezing point of water at 32 degrees Fahrenheit. So here in the US, that's when we expect a snow day, typically. And then the boiling point of water is 212 degrees Fahrenheit. Now, the difference between those 2 temperatures is 180 degrees. Now let's look at Celsius. So the freezing point of water in Celsius is 0. Much easier to remember. And the boiling point is 100. Also much easier to remember. And the difference between those 2 values is 100 degrees. Now for Kelvin, again, all of the values are positive. So this is based off of something called absolute zero. And absolute zero is a state where nothing is moving at all. Everything is completely frozen. Now, this is a somewhat hypothetical situation. So absolute zero might not actually be able to exist, but if it did, absolute zero in the Kelvin scale is 0 Kelvin, which makes sense. In Celsius, it's negative 273, and in Fahrenheit, it's negative 459. So again, in the Kelvin scale, all temperature values are positive. So water freezes at 273 Kelvin and boils at 373 Kelvin. So again, we have a difference of 100. Now, how do we relate these scales to each other? Well, Kelvin and Celsius is really easy. Notice that the difference between the freezing points between Celsius and Kelvin is 273. So the conversion here, Kelvin is equal to degrees Celsius plus 273. Super easy, not a bad conversion at all. However, if we want to convert between Celsius and Fahrenheit, it's much more complicated. So the way we do this is we look at the difference between the freezing points of water. So 0 versus 32. So if we want to convert Fahrenheit to Celsius, we have to subtract 32 from our temperature in Fahrenheit. And we also have to take into account the ratio of the degrees here. So we have 180 degrees between the freezing point of water and the boiling point for Fahrenheit, and for Celsius it's 100. Now, if we take that ratio, it comes out to 5/9. So we're also going to multiply by 5/9, and that'll give us the conversion here. Now, on an exam or a quiz, I would give you these conversions or these equations. I don't expect you to memorize them, but I wanted to explain where the equation comes from, because it can be a bit confusing just looking at it. So let's actually practice doing some temperature conversions. Let's convert 98.6 degrees Fahrenheit, which is body temperature, to Celsius. And then in the next problem, room temperature is about 22 degrees Celsius. Convert that to Fahrenheit. So see if you can do this conversion on your own first, and then we'll go over it together. Okay, so let's start with the first problem. So we're trying to convert Fahrenheit into Celsius. So we're going to use this equation up here. Let me get a different color marker. So we're just going to plug in our value of Fahrenheit into this equation. So that would be 98.6, and we're subtracting 32, and then we'll multiply that whole thing by 5/9. So when I plug this into my calculator, I get 37 degrees Celsius. All right, so that would be body temperature in Celsius. Now let's go to number 2. In this one, we're actually doing the opposite conversion. So we have 22 degrees Celsius is equal to degrees Fahrenheit minus 32 times 5/9. Okay, so we might need to do some algebra here to solve for degrees Fahrenheit. All right, so how can we move that 5/9 to the left side of the equation? Because we ultimately want to try to isolate that degrees Fahrenheit. Well, we can multiply by the reciprocal of that 5/9. So we'll flip our fraction. We'll multiply by 9/5 on both sides. All right, so then that would give us 22 times 9/5 is equal to degrees Fahrenheit minus 32. Okay, so now we need to get rid of that 32 on the right and move it to the left. So we can just add 32 to both sides. Okay, let's see. We're probably going to want to put parentheses around our multiplication there. So our final result here, we get that degrees Fahrenheit is equal to 22 times 9/5 in parentheses plus 32. So if we plug that into our calculator, we should get 71.6 degrees Fahrenheit. Okay, so let's do one more practice problem. Let's convert 98.6 degrees Fahrenheit to Kelvin. So pause the video, see if you can do this on your own first, and then we'll go over it together. All right, so on the last slide, we already saw that 98.6, oops, my pen stopped working. There we go. 98.6 degrees Fahrenheit is equal to 37 degrees Celsius. So we already did that calculation on number 1 on the last slide. So if we need to convert that to Kelvin, we can now just use this equation. So Kelvin is equal to 37 plus 273. So that should give us 310 Kelvin. Now, luckily for us, when we're in the lab, we're going to use thermometers that are in degrees Celsius, and then we can very easily convert that to Kelvin if we need to. And again, we'll just use this really easy equation. All right, so I think we'll stop there for this video. In the next video, we'll look at how we can calculate the amount of heat that's transferred from one object to another. So I will see you then.